Hello, and in this video I'm going to look at the Taylor series of the natural logarithm function. So a Taylor series is basically where you have to find the nth derivative in either case. So we kind of looked at that with respect to Taylor polynomials. So what we'll do here is we'll just consider the function f of x equals to natural log of x. And here we're going to center the value at, or the function at x equals to 1. Now, notice that if we plug in 1, we get that that's going to be natural log of 1, which is equal to 0. Take the first derivative, and in this case you get 1 over x, which if we plug in the value 1, we get that that's just equal to 1. Take the derivative again, and basically you get negative 1 over x squared, and then you get f double of x. Actually, it will be f double of 1 is equal to negative 1. Okay, so we have 1, negative 1. And then if we find the third derivative at x, well, this is going to be positive 2 over x cubed. But then when we plug in 1, we get that that's going to be just 2. Okay, now let's go ahead and find the fourth derivative. The fourth derivative at x is going to be negative 6x squared, and essentially when you plug in 1 into the fourth derivative, you're going to get that it's going to be negative 6. Now what do I need to do with this? I basically need to plug this into my equation where I have f of x is equal to the first value, so that'll just be 0, plus the second value, which will be 1 divided by 1 factorial, and then it's going to be times, so we said actually that it'll be x minus 1, right? So that'll be x minus 1 to the first power, and then that'll be plus, okay, so our second value is negative 1, so we have negative 1 divided by 2 factorial, and that's going to be, let's see, x minus 1 to the second power. Okay, now notice that if we go ahead and we plug in the third derivative, well, the third derivative is 2, so it's 2 divided by 3 factorial times x minus 1 cubed, and then we have that we did get the fourth derivative at 1. It was actually negative 6 over 4 factorial. And in actuality, if you look at it like this, well, notice that essentially if you look for the nth derivative at x, it's going to be basically n factorial. So you have that's going to be n factorial, but see like how it switches from positive to negative? So in either case, we have that we can come up with a formula that defines our nth derivative in either case. So so I have that would be, let's see, well, we started at k equals 0, right? Okay, so it looks that our formula, is n factorial divided by x to the n plus 1. Okay, so, but here we're just plugging in 1 basically, and notice that it switches in sign, so negative 1 to the n. N plus 1 actually. Okay, so if we plug in the derivative, the 1 into the nth derivative, you're going to get n factorial divided by 1 times negative 1 to the n plus 1. Okay, but here, notice that in general, like notice that this is kind of like n plus 1 factorial. And then that's kind of like n plus 1 in either case. So when we do the next term, so basically what we're doing is we're just plugging this in and dividing this by basically, yeah, so basically this would be kind of like n plus 1 factorial, and then you're multiplying this by x minus 1 to the nth power. Okay, but in either case, like if we go ahead and we simplify this, this will give us that you're going to get x minus 1, and then you're going to get minus 1/2 x minus 1 squared, and then this is going to be plus, well, this is actually going to be plus 1/3 times x minus 3 plus, okay, yeah, we missed out on basically this last one, right? Okay, so this last one was supposed to be x minus 1 to the 4th power. So this is going to be, and yeah, we need to make that a negative. So we'll make this a negative, and let's see, 6 into 24 is 4. So we have 1/4 times x minus 1 to the 4th power plus. Now at that point, we just need to add the last term. So the last term is basically found by just using our formula that we found over here. Now another case, let me see. Yeah, so in either case, what we can do here is we'll just use that it's going to be negative 1 to the n plus 1, okay, but divided by n. Because either way, if we substitute this into here, basically you're going to get that the factorials cancel each other out and it leaves you with just a single variable. Now depending on which way that you look at it, it could be n plus 1 in either case, which that's what I'm going to write here. I'm going to write n plus 1. Let me see. Actually, we can just do 1. Yeah, so let's just do n. And then this is going to be multiplied by, let's see, so we need to multiply this by x minus 1, but to the power n. Maybe I will go ahead and correct our nth derivative, actually. So if you kind of look at the nth derivative, notice that basically that's 0, and then that's going to be 1, 1, 2. So really the pattern begins after the second derivative in actuality. So you would have to use that this would be n minus 1 factorial. That's how we get that this cancels out. So in either case, like I kind of re-indexed it by saying use n plus 1, but I mean it's really the same in either case. Like it's kind of like bookkeeping if you think about it, because in actuality, when we plug in 2, we need that to be smaller. So in actuality, that should be n minus 1 factorial. So let me just change that for the nth derivative. Okay, so basically what we're saying is that the nth derivative of the natural log function is going to be n minus 1 factorial, and then basically this is divided by x to the n plus 1. Okay, but you also need to consider the sign of the nth derivative, which in this case would be negative 1. So it would be, so when I plug in 2, I need to get that it's negative, basically. Okay, so essentially that'll work if we use the same value of negative 1, but to the n plus 1. So that's why in this case, like when we plugged in 1, we figured out that basically that the nth term at 1 is n minus 1 factorial multiplied by negative 1 to the n plus 1. So essentially we get the same thing, because if you divide this by n factorial, because that's the nth term, that's where we get that that's going to be negative 1 to the n plus 1, and then that's divided by n. So in either case, like, we have our Taylor series. So if we go ahead and we write our Taylor series of the natural log function, that's going to be natural log equals to the series summation from k equals 1. So in this case, that'll be just 1. Oh, and yeah, that just keeps going, right? So that'll be from 1 to infinity, because, yeah, in this case, we just reindex it again. So this will just be negative 1 to the n plus 1. Actually, we're using k's, right? Okay, so we'll just use a k plus 1. And this is divided by k. And then this is x minus 1 to the k. Now, notice that if you wanted to find, for example, the natural log of 2, this would be equal to the series summation of negative 1 to the k plus 1 divided by just k, which that'll go from 1 to infinity. Now, basically what you've learned so far is that this series representation of natural log of 2, it converges, but it converges conditionally. So this equation right here, it converges conditionally, due to the fact that if we look at the absolutes, that will be a divergent harmonic series. Okay, now it would be interesting actually though to determine like the interval of convergence for, say, for example, natural log of x. And basically what you're going to find is that if you use either the root test or the ratio test, you're going to find that it will give you the interval of convergence in either case, which is more than likely going to be where it's from 1 to 2 in either case. But yeah, I'll leave that to you to see in terms of, like, you know, finding the interval of convergence. Maybe it is from maybe it is from 1 and it's a little bit larger, like in either case, in terms of like the interval of convergence. Because if you plug in 1, I mean, that should give you 0. So then we know that it's going to converge either way. But I'll leave it up to you in terms of like finding the interval of convergence for the Taylor series of the natural log function. But notice that if we go ahead and we look at the graph of the series, in either case, for the natural log function, that if it's centered at 1, then in either case we can still estimate values depending on the degree of the polynomial. Well, the idea is that for the infinite series is that basically n has to be very large, which if we were to extend it here, then in that case we would get that the polynomial is trying to fit on the curve. So we see that here the curve, it kind of goes away from the function natural log of x. But in either case, as long as we're close to the value, the center point, in this case 1, then our estimate is actually going to be a good approximation in either case. But look at this. If I go ahead and I use natural log of 2, then in this case, in looking at natural log of 2, I get that it's 0.6907 for the estimate. But of course, I can actually, you know, plug in natural log of 2 and say, for example, like we do natural log of 2, and we get it's 0.6931. Look how much we're off by. But again, the whole idea is that if n is really big, then we can actually improve that estimate for something like natural log of 2 in either case. But yeah, go ahead and try to find the interval of convergence for the natural log function, and essentially you'll see the values of which that it would converge at in any case. So use the ratio test or use the root test for determining interval of convergence for the logarithmic function centered at 1.